Good morning. Time to start another chapter. This chapter is all about naming compounds, putting compounds together and identifying how do we end up with formulas like H2O? How do we end up with formulas like NaCl? How do we end up with those? And then how do we name them? Why do we end up with the name of, sodium chloride for NaCl? So that's what we're going to look at in this chapter. But to start off with, we're going to start with the notes. Look like this. It said areas of the periodic table. So we're going to go over that one. If you notice at the top of those notes, I gave you like a really brief sketch of the periodic table. And, oh my goodness, where'd my periodic table go? Hold on. There it is. I'm going to use my camera. So to start with, in that sketch, and again, it's only got to be a sketch. I don't want you to like draw everything that's there. It's just identify that there's this region over here with two or groups going up and down here. And then we have this area in the middle of the periodic table. Then we have this area over here on this side. All right, and then we have the area that's down underneath the periodic table. All right. So those are basically, there's four regions to the periodic table. And if you remember from the last chapter, if it was a 2, it was the last spot, then we looked in here. If it was a 6, then we looked over here. If it was a 10, then we looked in the middle. And if it was a 14, we looked down below. So each one of those different areas on the electron configuration had a name for the orbital. This was the S area. This is the P area. This is the D area of the periodic table. And this is the F area of the periodic table. So we can name the area of the periodic table based on those orbitals that we put the electrons into. So that's one way in which we can organize the periodic table. So hold on, I got my pen that I used to point with. So that's one way, and that's really the first part of these notes. We're going to look at ways in which we can take the periodic table and break it up into groups. And one is the S, the P, the D, and the F. The next one, which is in the notes, is by representative elements. The representative elements, that's actually the S area, so it's this one, and it's the P area, so it's this area over here. So it's just those two areas, those are the representative elements. They're also called the group A elements, so you may want to know that also. A lot of times on periodic tables, you'll notice at the top they'll have this as group 1A, then 2A, then it's 3A, 4A, 5A, 6A, 7A, 8A is another way that they can be designated. Then the next group is the transition elements. That's this red area in the middle. It's the D part of the periodic table. That's 10 wide. They're also called the group B elements, and you'll commonly notice that there'll be a label across the top of 1 through 10. They're kind of mixed up a little bit, but they'll have a B after them. So instead of being group A, it's the group B elements. And then we get to the inner transition elements. That's these guys down below down here. They are the F region of the periodic table, and there's 14 wide. Now, why do they call them inner transition? If you notice over here, there's a little line that goes up. What's really supposed to happen is this whole region of the periodic table is supposed to slide over, and then the F region should go up in between here. Right? It's really not, and we always reference it as the area of the periodic table that's below the periodic table, but it's not where it's supposed to be. It's supposed to be up inside. That's why it's called inner transition elements. So why do they put it down below? Well, so it takes up less paper. It's easier to put it on a piece of paper like this than to make this piece of paper way wider and make it really, really long and make it so it doesn't fit in like folders and books and everything. So that's why they put them down below, and they do call them the inner transition because they're inside the transition elements right in here. So again, if you look at a periodic table, you'll notice that it references that they're supposed to go in here. All right, so that's another way we can break it down. So we can go S, P, D, F. We can go the group A elements, representative elements. We can go group B, transition elements, and we can go inner transition elements. Then we can also take this periodic table and we can divide it into halves. And the way in which I like to describe this is when we divide it in half, it's kind of like the way in which my wife divides my Snickers that she buys for me every so often after school. And I'm like extremely fortunate, right? Because when my wife divides the Snickers in half, all right, here's my Snickers. There's my Snickers that I get after school or that she buys for me. And when she breaks it in half, she breaks it in half like right here, all right, which is not equal halves. But again, I told you I'm extremely lucky. right? Most people would say, oh yeah, your wife takes the big spot and she gives you the smaller area. Nope, that's not what my wife does. Because again, I'm like really, really lucky. I don't even ask her to do this. This is the side she takes, and then she gives me this one, and she always gives me that bigger half of the Snickers bar, right? Now, why in the world am I telling you this in regards to the Snickers thing? Is because that's what we're going to do in this periodic table. We're going to divide it into halves like my wife does the Snickers bar. So we're not going to divide it into halves right here in the middle. Nope. What we're going to do is we're going to divide it right along this line right here where you see it's purple and blue. So we end up with 1/2 is this area over here. That's my half of the Snickers bar, the big half. And then we got this little bitty half up here. That's my wife's one bite of the Snickers that she takes, and that's it. That's all she takes off of my Snickers bar. All right. So this is 1/2, and this is the other half, the big half. All right. Now what we end up with is the left-hand side. Yes, I'm sorry. I'm looking at the periodic table backwards. I'm going, wait, that's the wrong side. But I'm looking at it backwards, looking at the screen. But the left-hand side of that periodic table, those are metals. And one way in which you can remember that those are metals is iron. I hope you know, is a metal. It's what your car is made out of. So that's on this side over here. So that would mean if that's a metal, then all the rest of these guys are metals that are over here. All right, including sodium, that's in salt, calcium that's in milk. Copper that's in your wires, silver, necklace, gold, all those are metals, right? So that's everything that's from this line right here and over, including the inner transition elements, because remember, they're actually supposed to be right in between here. All right, then we got, and these guys on this side, they are good conductors of electricity, right? They all will conduct electricity to some amount. There are some that are better than others. The best ones are copper, silver, and gold in that same vertical group. That kind of also indicates that vertical groups have similar properties. Why? Because their electron configurations are very similar, right? But all these can conduct electricity. One exception on this side that is not a metal, this guy right here, hydrogen. Hydrogen likes to act like a metal, but he's actually a non-metal that we're going to learn about in a second. All right, guess which one's probably going to be on the test? Hint, hint. All right, is hydrogen. All right, hydrogen is not a metal. He's a non-metal, but he likes to act like a metal. All right. All right, then we go to the non-metals. Non-metals, that's this green region over here on this side. Not very many elements, but there's a few in there. They make up a lot of stuff that surround us, actually, that we'll learn later on. But non-metals, that's the right-hand side of the periodic table. They are non-conductors of electricity. They don't conduct electricity very well. So that's the stuff that's on the right-hand side. So we got metals over here, non-metals over there. Then there's the ones that go right down this stair step. And those are neither metals nor non-metals. They're halfway in between because they're between the two regions. And they're called metalloids or semi-metals. And they happen to be, and I listed them in your notes, but it's boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine. Now notice I left one out on there. I left out aluminum. Aluminum is another exception. He's not a metalloid or semi-metal. He actually is a metal because he's on this side. Gosh, guess which one's going to be on the test also? We said hydrogen and probably aluminum. So remember, even though aluminum's on the stair step, he's not a metalloid or semi-metal. He's a metal. Now, one of the traits that these metalloids do, remember we said that metals conduct electricity, non-metals don't. These guys kind of conduct electricity. So they are called semiconductors. And one of them that you would say is probably really, really important in your life is this guy right here, silicon, which, what does it make? It makes computer chips. So it makes all the computer chips that are in your phone, in your video games, in your laptop, in your computer. It's in our cars, inside the computers in our cars. So everything that's got a computer has silicon in it, all right, because we utilize that semi-conduction ability of that. So it kind of conducts electricity, and we can use that in order to make the little switches turn on and off that we talked about in the measurement chapter. That's the way in which it is utilized inside of computers to make it so that we can do all the things we do with our phones and our games that we play at home. So this guy is really, really, you would say, is really, really important to your life. I'll tell you, no, all that stuff is not that important to our life. We can live without it. But that's neither here nor there. So, all right, so that's another way to break up the periodic table. So we've got S, P, D, and F region. We got representative elements, which is A group. We got transition elements, which is a B group. We got inner transition elements. We also got metals on this side. We got non-metals on that side. We got semi-metals, metalloids in between. So we've got some different ways in which we can break up the periodic table. All right. Now the next piece of notes has to do with a thing called ions. And we talked about ions right at the end of the last chapter, just briefly to give you a little taste of what ions were all about. What ions are, I'm going to put this thing down for a moment. Ions are atoms that have a positive or a negative charge. Now, why do they have a positive or negative charge? It's all because they either lost or they gained electrons, which was on that last test. It was also in our notes. Or if it loses an electron, then he has more protons, more positives, so he ends up becoming a positively charged atom. If he gains electrons, pulls some electrons in, they're negative, so now all of a sudden he's got more electrons than he does protons, so he's going to be negatively charged. Right? Now, what I want to do is we're going to diagram some atoms really quick in your notes. Okay? And what we're going to do is we're going to do a period going straight across on the periodic table. That's why it's called a periodic table, because the groups going crossways. They are periods. Ones that go vertical, they're called groups. So we're doing the period that has lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Right? And those are the ones that are in your notes, actually, to be able to look at. So we do lithium to start with. Well, lithium happens to have 3 protons, and he's got 3 electrons. What I tried to draw on there was to try and show you is that he's got 3 protons, and then we have this. And I put down first and second, right? And I didn't actually make the boxes because the computer didn't like me trying to do the boxes, but I left the boxes off. So in the first one, he's got 2, and the second one, he's got 1. That's what I put in there. And then I put down, remember when we talked about it last time, we said they want to have 8 in that outermost ring. Now, this one's kind of, there's a weird exception to this, which I think you'll get it in a second, and that is, for him to get 8, he would have to bring in 7. That's a lot of electrons to pull in. Or what he can do is he can get rid of that 1, give it away. So now he has nothing in this outermost ring. So that takes him back down to this. But wait a minute, Mr. Pape, you say he's got to have 8 in the outermost ring. Well, can this ring have 8? No, the most it can have is 2. Is it full with 2? Yes. So that makes this atom happy. These atoms are the only ones that are unique in the idea that they don't try and get 8, but they try and get that lesser energy level that is full. All right, and that makes them happy. So this guy loses an electron, and if you notice in your note, because he loses an electron, he now has 3 protons, 2 electrons, so it's a positive 1 charge. All right, then we go to beryllium. Beryllium has 2 and 2, so he's got 2 in his outermost ring. So he's going to take those 2 electrons and give them away. All right, so that's going to be this spot right here. I'll get rid of this now. So he's going to have a 2 in here. So he's going to go, it's got to pull in 6 or get rid of 2. I'll get rid of 2. So now he's got 2 extra protons, so he ends up becoming positive 2 charge. Then we get to boron. All right, and boron, he happens to have a 2 and a 1 in that ring. So he's got a total of 3 out there. So he's got to pull in 5 electrons to get up to 8 or get rid of that 2 and 1. So he gets rid of that 2 and 1. And now he's got a positive 3 charge because he's got 3 extra protons. Then we go to carbon. Carbon's got a 2 and a 2. So he's got a total of 4. Oh, now this is tricky. 4 is half of 8. So what this guy will do is he'll either pull in an extra 4 to get himself up to 8, or he'll get rid of that 4. Right? So because of that, what we end up with is we end up with a positive 4 or a negative 4. So we consider carbon to have a positive or negative 4. Because he'll either gain or lose 4 electrons, depending upon his what he's going to do with other atoms that are out there. Right? Now we go on to the next one, which is nitrogen. He's got a 2 and a 3. So he's got a total of 5 electrons. So with 5, he needs to bring in 3 more. So he'll bring in 3 more to fill this. When he does that, it ends up becoming a negative 3. All right, hold on, I gotta click off because I'm just about to my end of my time. So we're gonna go on to part number 2, and then I'll finish up with the next 2.